Hello all, I am your TA Balaji and today we will be discussing the solution for assignment 4. Question 1. In inverter, if Wn is made k times Wn and Wp remains unchanged, the trip point Vm, the given answer is decreases. So intuitively we know that in a given inverter, if you have an NMOS whose size is increased, then the trip point of the inverter will decrease. So mathematically we can also prove it by looking at the short channel equation for Vm over here and as well as the long channel equation, and we've just sweep gamma, where gamma is basically kp dash Wp by kn Wn from a certain low value to a high value to observe the trend. Basically for a low value indicates a high kn Wn and a high value indicates a high kp Wp, right? So that's what we've done here. If you observe that this is swept from 0.005 to 3 in steps of 50, right, which is multiplied by value of kn kpwp by kn wn, and you can see that the Vm has an increasing trend from the left to the right. The same holds for the long channel, same holds for the short channel as well, right? So just give you a moment to observe the code here, which is the Python code that is written to implement these two equations. Yeah, hence we can mathematically say that decreases. Question 2. The gain of an inverter at the trip point is minus 40, where we use the noise margin approximate model with suitable assumptions to VOH and VOL. What is the value of NMH? So to calculate NMH, we know VIL is this, right, and VIH is this. So now NMH is nothing but VDD minus VIH, right? So when we calculate VIH, it comes out to be 0.9225, and NMH is as shown here, which is 0.8775, and the given answer range is 0.8755 to 0.8795. Yeah, that's question number 2. Just give you a moment to look at the equations. Question 3. What is the value of delta VILH for the reference inverter? VOL is so much, VOH is so much, right? So VIL can be written as this and VIH can be written as this, and when we write down the expression for delta VILH, we subtract VIH and VIL, and we obtain this expression. Okay, so if you go back and calculate what gamma comes out to be, it will be 1, and we calculate delta VILH to be 0.15. Just give you a moment to look at this expression. Question 4 is a similar question, wherein the values turn out in such a way where VOL turns out to be VDD minus VOH. Now when you go and plug this back in here, so if you see VOH minus VDD is nothing but minus VOL. So you can substitute that back in here and you'll obtain 2 VOL plus 2 gamma into VOL. In our case, gamma is equal to 1. So 4 VOL divided by 2, which is 2 VOL. So the answer simply turns out to be 0.2 for question 4. Question 5. So the previous state of this capacitor was VDD, and we've been asked what happens to the capacitor's voltage at infinity, right? So if you look at it, this pass transistor can pass the value of VDD directly. However, if there is a current path from this capacitor to ground, it will be active only unless and until it will be shut off if some transistor over here goes to off mode, since they've been assumed as ideal transistors, right? So what will happen when the value of the voltage comes as close to mod VTP here, right? So the on value for this is nothing but 0 minus minus, let's say, VTP, right? Minus mod VTP. So it would be it would be mod VTP. So we need the transistor to be at least mod VTP for it to even conduct some amount of current. So the current will only be conducted until the value of voltage is at mod VTP. Otherwise, if it goes lower than that, it will be 0. So basically the maximum voltage the capacitor can be with the given constraints is mod VTP, right? In figure 2, however, you can see that VDD, you can see that in the previous question you could see that this node formed the source and this is the gate. However, in this case, this is the source node and this is the gate node, and it always has a constant VSG. Therefore, the flow of current will never be stopped no matter what the voltage of this node is, right? So the voltage of this node would come up all the way up to VDD, right? Because this node is at VDD, so the capacitor will be charged up to VDD. So in the previous case, it would be at mod VTP, and hence the answer will be this. Question 6. In the previous question, the transistors were not ideal. The transistor have leakage current. What would be Vc of infinity? So if this transistor had leakage current, obviously at infinity, the leakage current would be the path for any current to basically flow and the voltage to be dropped at this node, and hence the voltage of this node can go all the way to 0, right? So 0 and VDD will be the right answer. Question number 7. In the above figure, NMOS is considered a long channel device that does not possess channel modulation, Dibble, and velocity saturation effects. At t equal to 0, its gate is instantaneously raised to VDD from 0. Determine the equivalent resistance of NMOS, right? Okay. So now if you go back and refer to the slides, the R equivalent is given as this, where I naught is nothing but this, right? Because it's a long channel device. Now given that it's a long channel device, we go back and substitute all the values over here, and we obtain the current to be 420.5 microamps, and R equivalent is 3.21 kilo ohms, right? So 3.2 to 3.22 is the allowed range. Question 8. In the above figure, NMOS considers a short channel device that does not possess channel length and Dibble. Now what is the equivalent resistance of the NMOS, right? So in question 9, in question 8, in question 8, this is the equation that you would use. Since it doesn't have any channel length modulation, this is the equation that you will use for a short channel device, and you obtain the current to be so much. And the R equivalent will come out to be 6.75 kilo ohms. Question 9, however, you say short channel device does not possess Dibble but has channel length modulation. Since it has channel length modulation, you can go back to this equation and plug in into 1 plus lambda VDS, and this is the current that you will obtain. And again, R equivalent will also have the respective lambda term in it, and you can go back and plug in and calculate the value, for which you will get 6162.5 ohms, which you have to write in kilo ohms, which is 6.162 kilo ohms, right? And that is definitely falling in the range here. Okay, so I'll just give you a minute to look at question 8 and actually question 7 to 9. Yeah, moving on. Question 10, right? The Elmore delay tree, let the delay t at node n2 correspond to so much. If r2 is doubled, then the delay at n2 is. So question 10 has n2's delay given as t, right? So the node delay of n2 can be written using Elmore's delay as follows, right? Which is 4k square, and tau 2 dash is where r2 is doubled, right? And that can be written down as follows here. And we have been asked what is tau 2 dash by tau 2, which is 1.25 times tau, which is tau 2 dash. Basically tau 2 dash is 1.25 times tau. So this is basically applying Elmore's delay and calculating the values, right? So I'll just give you a minute to look at this. Yeah, similarly for question 11, we've been given that if an R3 is tripled and C3 is half, then the delay at node N2, right? So the delay, again you will go back and you can write down what is tau 2, and we see that we obtained 4k square, which is the same as what we had earlier, so there's no change, right? And hence the answer remains the same. In question 12, we've been given values here, and we've been asked for derive the estimate the propagation delay from n1 to n3. So in question 12, basically you will write down the values of r1, c1 and all these constants, and finally you will say 5 times rc, which is 4k into 8, and you will obtain 160 picoseconds. That's here. And question 13 is again you will go back and write the Elmore delay value, which is as shown here. From n1 to n4, right? So basically when you have to write the Elmore delay value, so I hope that is clear. The way you would write it is, for example, let's take question 13. From n1 to n4, let's say this is the path. The way you would write it is, you write C1, you have capacitor C1, C2, C3 and C4, but to all of those capacitors you will only have to add the resistances that it sees during the path, right? So C1 sees R1, then C2 sees R1 and R2, but C2 sees R1 in the path but not R2. C3 sees R1 and R3, and C4 also sees R1 and R3 in the path. Though it has R4 here, it should not be considered because the path is only this much, right? So if you write it like this, that's how you get 192 picoseconds. You could apply it even for the other questions, and I'll give you another example with question 14. We've been asked what is n1 to n5, right? So the path, if you look at it, it is like this, and now you can write down C1, C2, C3, C4. But what are the resistors in the paths? For C1 it would be R1, for C2 it would be R1 again, for C3 it would be R1 and R3, for C4 it would be R1, R3 and R4. Okay, so yeah, this is how you would write it. So given this, that's what I've written over here, and you'll get 224 picoseconds. 4 picoseconds, yeah. I'll just give you a minute to look at all of these calculations, and that's how we would go about writing it even for the previous questions. Yeah, thank you all.